Hello, everyone. I'm Marco Slot. I work at Crunchy Data, and I'm going to talk about a journey we've been on for the past 18 months to build a Postgres data warehouse. So, if you're interested in using Postgres for analytics, or you want to know more about what's possible using Postgres extensions, this will be a very interesting talk. Now, a lot of you might know me from my days in Citus. I've been working on Citus for most of the past 11 years, so it's a big big chunk of my career. Um, and when we started Citus, we were actually looking at going into the analytics space. At the time, you had Hadoop and Spark SQL had just appeared, and we were thinking, oh, can you do distributed queries on large amounts of data using Postgres? But pretty quickly, it became apparent that it was more natural for us to go after workloads where Postgres was already a good fit, like software as a service workloads that needed to scale out. And also, these were real time analytics workloads where you're writing a lot of events into the database and you're doing some pre aggregation in the database and have a lot of queries on the pre aggregated data. But it wasn't really a good fit for sort of more general analytics, business intelligence, where you combine data from lots of different sources and do transformations and complex queries across all the data. But still, a lot of the companies we talked to were actually looking for a Postgres data warehouse. It was just, I mean, we would have liked to build something like that for them, but it's also very hard because fundamentally, Postgres is an OLTP system. I mean, the database industry is sort of divided into these two factions, some smaller factions, but the two main factions are OLTP databases and OLAP databases. So these are different systems, different people. They don't talk to each other very much, but they do agree that you should use SQL, that you should have transactions. But everything else is a little bit different between these databases. So OLTP systems like Postgres, they focus on supporting a high rate of transactions, like small updates, update a single row, select 10 rows with very low response time and very high throughput. Whereas analytics databases, they don't necessarily handle many queries at the same time or queries at a very high rate. Instead, they focus on having a very high scan throughput. So scanning through lots and lots of data in a single query very quickly. And this is a very different kind of optimization problem. Like in OLTP, you want a very quick planner. In analytics, you want a query planner that can really find the best possible query plan. And if you start zooming in the details of these systems, they're really different at every level. But one of the most sort of talked about difference is the storage format. So OLTP systems generally use row-oriented storage. So the data stored row one, row two, row three, and then there is an index that you use to find a specific row or a small set of row. And the index only requires you to take a few steps, and that's very efficient for running queries that select by a unique key, for example. Analytics databases tend to use column-oriented storage. So values from the same column are stored together on disk, often in a compressed form, because maybe some columns only can contain mostly zeros or some recurring strings. So it tends to compress pretty well. And then analytical queries, they often span many rows, but maybe not all of the columns. So in this case, you only have to read the columns that you actually use in the query. But the big performance differences between these systems partly come from how they execute queries. So a row-based system will typically take a row from storage, and then in the query is essentially a set of expressions like from the where clause and from the select clause and the aggregates. And so it will take that row, evaluate the first expression, the second expression, the third expression, take the second row, first expression, second expression, third expression. And all these expressions are a bunch of function calls that do a bunch of allocation. So there's a lot of CPU instructions associated simply with switching between different functions. Because of the allocations, your CPU cache might not be used very efficiently. And your CPU also has a hard time predicting what's next because one of the ways CPUs speed up programs is by kind of already going into the next instruction before the previous one has started. So in column-oriented systems, what you can do is this vectorized execution. So there, the query engine takes a vector of values, an array of values, and the expressions are all implemented as loops. And so they do the same comparison on all values in the vectors. And outcomes may be a new vector with, let's say, the indexes of the rows that match the filter. And now this function call overhead almost goes away. You only switch between expressions once every, let's say, 2,000 rows. Your CPU has a better chance of guessing what's next. You keep the data in your CPU cache. And then also modern CPUs have these instructions that can process multiple values in a single instruction. And altogether, especially combined with parallelism, these databases can often be 10 or 100 and sometimes even more than 100 times faster than Postgres for analytical queries, which is pretty amazing, and it's also hard to scale against. Um, but it's very hard to build a vectorized query engine. There's also the fact that other parts of Postgres are not necessarily optimized for analytics. So you wouldn't want to put in all the effort of building a very good vectorized query engine and then find that it doesn't work well because Postgres is not architected for it. But of course, Postgres has one important superpower, which is it is extensible. So anything that Postgres is not good at, we can make it good at through extensions. A few years ago, it was not a good vector database, but now it's a great vector database because we have pgvector. It was not a distributed database, but then Citus made it a distributed database. And similarly, we can actually make it a good analytics database through extensions, but we do need a vectorized query engine. And over the past few years, we've seen the emergence of these embedded query engine. And I think DuckDB for our purpose is actually the most suitable one. It has a similar license to Postgres, it's targeting single machine. And its SQL dialect is actually derived from Postgres. That it uses the parser library that's derived from the Postgres parser. And it also has extensions itself, kind of inspired by Postgres, which makes it more amendable to being integrated into different environments. So we can now feasibly build a data warehouse with DuckDB, this vectorized query engine, to speed up the analytical queries and use extensibility to integrate it into Postgres. Because one of the things that Postgres allows an extension to do is intercept all of the incoming user commands at different points. So, for example, there is a hook to intercept all of the DDL commands or all of the queries when they are planned, or to intercept writes and do something different than what Postgres normally does. Very often, you check is this a query I care about? If not, I give it back to Postgres. But if it is a query you care about as an extension, you could do something else. For example, we could let DuckDB handle a part of a query, or we can handle DDL commands in a particular way or writes in a particular way. And that way we can build this notion of an analytics table into Postgres, where you still have your original regular Postgres heap tables, but now you also have an analytics optimized table, which uses vectorized execution when you query it. Now, how do we actually store such a table? There are actually a few different options. One is we implement columnar storage in Postgres, and we store it in the Postgres buffer manager and write ahead log. We've actually done this in the past with Citus columnar, and it works reasonably well. The problem is again that the Postgres buffer manager is not really optimized for analytical use cases. It's used these tiny 8 kilobyte pages and some locking on the pages. And then also it's not really thread safe. So we cannot have DuckDB, which is this multi-threaded query engine, uh, use the buffer manager to its full extent. So another alternative would be, can we use DuckDB's native file format? So we just put a file next to the Postgres directory, and then those tables are just stored in the DuckDB file. The problem is that Postgres often has replication, and so only the things that go into the Postgres write-ahead log are going to show up in a secondary node. So if we fail over to a secondary, the DuckDB file is just not going to be there at all. Um, Another option is we put the data into a separate storage, such as blob storage, object storage. And we could also have a cache on the server itself, so we can have some higher bandwidth, lower access latency, and then both the primary and secondary can talk to the same blob storage. And we can also keep some metadata in Postgres itself to remember which files are currently part of the analytics table. And we can use the Parquet file format in the object storage, which is a very popular format for storing data in a columnar fashion. It's basically like CSV, but columnar and with well-defined column names and types. So as it turns out, there already is a table format for that you can store in blob storage called Apache Iceberg. So Iceberg is a specification that describes a metadata layer. And the metadata files that also live in blob storage, they describe which Parquet files are currently part of the table, what's the schema of the table, what's the history of the table, what's the partitioning of the table. And then there's one top level file, a JSON file actually, that describes this is really the current state of affairs. This is the current table. And as you write to this table, you generate new Parquet files, you generate new metadata files, and you generate a new top level metadata file. And so if you want to query the latest version of the table, you need to know what the latest metadata file is. And that URL of that file is typically stored in what's called a catalog, but the catalog is basically a database. In fact, it can just be Postgres. So in our case, if we can create an Iceberg table format in Postgres, we can also act as the catalog. So we can just do our bookkeeping in local Postgres tables. And we can have a very nice kind of transactional Iceberg table format. And we can use the extension APIs to intercept writes such that we generate Parquet files and metadata files. And when the table is queried, we can use the hooks to let DuckDB handle part of the query, which makes it very fast. So we built an implementation of this idea called Crunchy Data Warehouse, which is basically Postgres with additional extensions to implement Iceberg and to also implement these data lake tables that can query CSV and JSON. And we often find this is actually 10 to 100 times faster than just Postgres tables on the same server for analytical queries because of DuckDB, but also because we use caching very aggressively. One of the nice things about Iceberg is that all the files are immutable, so you can cache everything. And we kind of moved away from the model. Like, so we still use extensions exclusively, but we moved away from the one big complex extension model that we had in Citus because, well, one of the things that has happened in the extension ecosystem is there's now Rust extensions. So if we have a constellation of modular extensions, we can have some of them in C, some of them in Rust. We can also say some of these are open source, like PG Parquet. Some of these are closed. And it also just helps us organize our code. So we quite like that model. So with these extensions, one of the things we're adding into Postgres is this notion of an Iceberg table. So you can just say create table using Iceberg, use most of the Postgres features like sequences, generated columns, triggers, constraints, just not indexes and foreign keys. And when you create a table, we'll write the metadata files, and then you can insert. If you insert a few million rows, it usually just takes a few seconds. But if you insert one row, it probably also takes a second because it does need to write a bunch of files into blob storage. So it's always good to batch things. But you can, for example, collect writes in a regular Postgres table and then move the data into an Iceberg table. Now, when you update an Iceberg table, so we'll use DuckDB underneath to scan the Parquet files of the Iceberg tables. And we'll ask it to give us the file names and the row numbers that match the filter in the query. And Iceberg has this notion of a position delete file, which defines which rows from the existing table get deleted. And those are basically pairs of file names and row numbers. So we can feed that information directly into a deletion file, and then the new rows go into a new Parquet file. We'll write the metadata files and update the catalog. And we can do a bunch of these updates in a single transactions across different tables, rollback, sub transactions, everything. And then when the table is queried, we'll we'll again use DuckDB to do a read Parquet. So this is just a function that DuckDB has to scan Parquet files, and then we'll filter out all of the rows that appear in these deletion files. So over time, you build up some table bloat, just like in Postgres, like rows have been deleted, and we're filtering those out when we query. But every 10 minutes, we run this automatic compaction process where we take small Parquet files or Parquet files that are heavily deleted, and we compact them together into new Parquet files. So this just happens every 10 minutes. So the way the querying works is, Postgres allows us to intercept the query planning process at multiple different stages and suggest alternative plans or kind of force it to use our plan. And so what we can do, the planner kind of goes. I see it as inside out, like from the from clause with the table scans, it goes outwards to the group buys and the order buys. So we start looking at a scan, which is like we're scanning this table, this iceberg table with some filters and some from projections, and we check, can this SQL, can we from the scan generate SQL that DuckDB can handle? If not, then we'll look at what it can handle and generate SQL for that. If it can handle everything, we move on to the next stage and check, can it handle the group by and the aggregates? If so, we'll move on to the order buys and the limits. And that way we kind of find the biggest possible piece of the query that it can handle. And for that, and we'll put that as a separate execution node in the overall Postgres query plan. So our query plan is actually a hybrid between stuff that Postgres executes and stuff that DuckDB executes. And sometimes there can actually be multiple DuckDB executions in a single Postgres query plan. And this way, we can actually support any SQL query and also make it as fast as possible. So this uses this hybrid architecture where the Postgres processes, like if you store data in a Postgres table, it still uses block storage like Premium SSD, but then DuckDB, it stores the Parquet files in object storage behind this cache on a local NVMe drive. And so there's multiple Postgres processes talking to one DuckDB process, so that we don't have this super high memory usage if we put DuckDB in every process. So altogether, like running ClickBench, which is a popular kind of single table analytics benchmark on a Postgres table and also on an Iceberg table, just on the same machine. Like the Iceberg tables go up to like 50, 60 times faster, especially with the caching. But even without the caching, we fetch just the pieces of the Parquet files that we need. That's one nice property of Parquet files, that you don't always have to download them fully. Also TPCH with more complex joins. This benchmark we ran 14 times faster with Iceberg. And we really like tweaked the hell out of Postgres here, adding all the indexes. Also, we used quite small scale factor. The difference is actually much bigger at bigger scale factors. So there's different ways in which we see people kind of using these capabilities. One of the ones that's been getting more and more popular is the sort of zero ETL log management. So, um, teams often have a lot of different types of logs in blob storage, and want to do some queries on those. And there's a lot of tools that give you a type of SQL to run on your logs. But if we could get the data into an Iceberg table, then you can just use Postgres queries to query your logs. So one of the things we can do now is we create a table that points to our logs. The logs might be in CSV or JSON format. We also support some more kind of text formats that need to be parsed. And so you can create a table that points directly to those files. You could already query them at that point, but because of the JSON parsing, it might not be very fast. But what we can do is create an Iceberg table. It could have the same schema, or we kind of select more specific fields from that we're interested in and extract those from the JSON. And then we have this open source extension called PG Incremental, which basically I previously created an extension called PG cron, and PG incremental is essentially a layer on top. So it periodically runs a command, but every time it runs it with a different parameter value. And that value kind of goes through some sequence of things. So, like after an hour, process the last hour, or process a range of sequence values. But you can also process new files showing up in blob storage. So when you run this command, it'll run this insert into logs Iceberg for all of the files that are already there in batches. And then whenever new files show up, it will run the command as well with those files as the parameter. And that way, and that's every time we run this is a transaction. So if something fails, we'll just retry those files. If it succeeds, we'll never try them again. And so basically in 3 commands, you set up this whole log pipeline and can now query your logs using Postgres, which is pretty nice. Um, but this is if the data source is already files in blob storage. So what if your data source is actually another Postgres server? Like you have data in your operational Postgres server and you want to run analytics on that. So a few weeks ago, we actually released logical replication from Postgres to Iceberg. Again, using purely extensions, though it was pretty hard, but you can now actually go into any Postgres server and create a publication. And then you can create a subscription in a warehouse server where you use Iceberg tables as the target. You can also ask it to automatically create all the Iceberg tables, which will set up all the metadata files. And then the data starts automatically copying in the background. And once that's done, it starts replicating the inserts and the updates, deletes, and truncate commands. It does micro batches, so it accumulates some of the changes in Postgres, and then it flushes those into Iceberg to generate the new Parquet and metadata files. That still generates some small files, so then every 10 minutes, those files are automatically compacted as usual. So I have a little demo of that setup that I'm gonna switch to now. So here I'm connecting to my production database, my operational database. It has a table with about a billion rows. I mean, synthetic data, but and let's say I wanted to do an analytical query, simple analytical query, and it takes 4 minutes, and it probably puts an awful lot of load on my database. So I don't want that. So what I can do now is create a publication with all my tables, connect to the warehouse, and then create a subscription with the connection string and the publication name. This goes and creates the Iceberg tables, and the data starts copying in the background. It takes a while. It's a billion rows. So we're kind of fast forwarding in the video. But now I can run that same analytical query and it finishes in 300 milliseconds. That's a bit idealized because I haven't had any updates yet. So let's run some updates using PG Bench. So these are transactions that do one insert and 3 updates, I think, per statement. So 10,000 writes per second total. And then on the right, you kind of see what happens with the Iceberg tables. Like they sort of sit in the same version for a while and then they jump forward because the changes have been applied. So that way we can kind of directly replicate from any Postgres server into these analytics optimized Iceberg tables. Um, and so in summary, You can turn Postgres into a data warehouse, into a modern data warehouse or lake house, as some people like to call it, with support for Iceberg, which has become the sort of the main table format in analytic systems, and also full transactions across Iceberg tables, across Postgres and Iceberg tables. We can make it very fast by integrating DuckDB and this write-through caching. I mean, it'll never be faster than DuckDB, but because you typically run this in the cloud and you have this extra cache, it pretty much goes as fast as possible. Then if you need to scale out, you can also point tools like Spark and Trino directly at the Postgres server and use it as an Iceberg catalog, and then Spark and Trino will pull the data directly from Blob storage. And I mean, there's a few different teams kind of pursuing this architecture. We were a bit early, so like we shipped the first production ready version last November. So let's see how it goes. It's a very exciting new motion in the Postgres space to add these analytical database engines directly into Postgres. So if you have any questions, feel free to ping me on Discord or send me an email or look me up on LinkedIn. We also write a lot about our projects and general Postgres tips and tricks on our blog. So also recommend going there. Thank you very much. Great to be part of another Posette.